Consider the reaction of the combustion of propane gas, C3H8. Combust means to burn or react with oxygen gas, O2, to yield CO2 gas and H2O liquid. The change in enthalpy is negative 2,221 kilojoules. This means the reaction is exothermic, or that heat is released in the process. But what if the change in enthalpy wasn't provided? How would we know the change in enthalpy? The good news is that enthalpy is a state function, and we can use the standard enthalpies of formation to solve for the change in enthalpy for the reaction. First, let's define what is the standard state and enthalpies of formation. The standard state is denoted by the degree symbol, and for compounds are exactly 1 atmosphere of pressure for a gas. For a pure substance in the condensed state, the standard state is the pure solid or liquid, and exactly 1 molar for a solution. For elements, the standard state is the form in which an element exists at 1 atmosphere of pressure and 25 degrees Celsius. For example, under these conditions, oxygen gas is in the gas phase, iron metal is in the solid phase, and bromine is in the liquid phase. Now, what is the standard enthalpy of formation? The standard enthalpy of formation is defined as the change in enthalpy for the formation of 1 mole of compound from its elements in the standard state. You'll notice the subscript F in the notation. For example, here is the standard enthalpy of formation for propane, C3H8. Notice propane is formed from its elements in the standard state, carbon graphite and hydrogen gas. The change in enthalpy is negative 104 kilojoules. This means that 104 kilojoules of energy in the form of heat is released when propane is formed from the elements. Now, let's return to our problem. The change in enthalpy is given. This value can be measured experimentally. But what if this value wasn't provided? Since enthalpy is a state function, we can use this equation. The enthalpy of a reaction is equal to the summation, represented by the letter sigma, of the change in enthalpies of the products, carbon dioxide and water in this example. Notice, each enthalpy of formation value is multiplied by the n term, which represents the mole coefficient of each product respectively in the balanced equation. In this example, 3 for CO2 and 4 for water. Then we'll subtract the sum of the change in enthalpies of the reactants, propane and oxygen gas in this example, each multiplied by their respective mole coefficients in the balanced equation. Now, where do we find the standard enthalpies of formation? Fortunately, many reactions have been studied over the years, and these values are well known to us, and you can find thermodynamic tables in various reference handbooks. Most likely, you can turn to the appendix in your chemistry textbook and find thermodynamic tables. The tables will look something like this. I have the 4 species for our reaction listed. For each species, you'll find the standard change in enthalpy of formation in kilojoules per mole. You'll also find the change in Gibbs free energy in kilojoules per mole and the entropy in joules per Kelvin mole. Gibbs free energy and entropy are both state functions. Thus, you can use the same equation to find the change in free energy and the change in entropy respectively. Let's go back to the enthalpy changes. As we've seen, the standard enthalpy change of formation for propane, C3H8, is negative 104 kilojoules per mole. Notice the standard enthalpy change of oxygen is 0. This is because oxygen already exists in its elemental state, O2, under standard conditions. The standard enthalpy change of formation for carbon dioxide and water are negative 394 and negative 286, respectively. Now, let's simply insert these values into the equation. Remember to start with the products. 3 moles of CO2 times negative 394 kilojoules per mole, plus 4 moles of H2O times negative 286 kilojoules per mole, minus 1 mole of C3H8 times negative 104 kilojoules per mole, plus 5 moles O2 times 0 kilojoules per mole. We can ignore the zero term for oxygen. Following significant figure rules means I'll round some terms, thus leading to very minor error. We obtain an enthalpy of reaction of negative 2,216 kilojoules. The percent difference is less than 0.1%, which is acceptable. Thank you for watching. You can find more lectures on thermodynamics in this playlist and enthalpy stoichiometry in this video.